Hi, my name's Eli Jacobson, and I'm on the basic utility vehicle drivetrain design team. This here is Matt Lonergan.
Craig Blau.
So, I see the drivetrain here. Tell me the basic elements of the drivetrain.
If you look here in the image, it uses a 10-horse Yanmar diesel engine, which is then going to go to a Comet CVT, which we had specially tuned. From there, it's going to go through a drive shaft to another gear reduction just via chain drive, and then it's going to output to the drive shaft, which will go to the rear end of the vehicle.
So it does have a differential.
It does have a differential.
Right in the axle.
Yes.
I'm looking here and seeing some calculations. Matt, what's your favorite piece of software?
Favorite piece of software? Microsoft Excel.
Is that what you used to design your driveline? So walk us through, what were the specs, torque, speed, or whatever. How did you design so that it will actually work in the end?
Okay. We start off pretty much with full throttle, which would be 3,600 RPM. We found the CVT that we needed by contacting Quality Drive Systems in California, and it actually gave us the biggest reduction that we could possibly get, which is 5.12 to 1. Starting from that reduction, we had to figure out how to get that power to the wheels, how to get 20 miles per hour top speed, and also how to get 1,000 foot-pound torque low end. So once we got that CVT, we had to figure out that somehow to get another reduction. So for that reduction, we used number 50 roller chain with an 18-tooth sprocket and a 72-tooth sprocket. And after that, it goes back to the differential, which has a ratio of 3.73 to 1. And just using a spreadsheet, we figured all that out. We learned that in Dr. Buckmaster's class.
What was the name of that course?
That's off-road vehicles.
Yeah, in Ag and Biological Engineering at Purdue.
Maybe.
So this is a cool vehicle because you can either go fast or you can pull hard. You get to do both. So Craig, it looks like they've got an electric front drive. How does that work?
The basic theory of operation is that we're powering an electric winch with current from the battery, utilizing the switch that's integrated in the actual package from the manufacturer. You can go forward or reverse by changing the direction you depress the switch. Basically, when you power the motor, you're going to be spinning this drum. On the drum, we have a sleeve that we have machined into a hub, which our 22-tooth large sprocket is welded to. Once the power leaves on this chain, it rides down to a sprocket and Lovejoy, which ride a brass bushing, which are free to rotate on the shaft. The actual engagement of the shaft is done by utilizing another outer Lovejoy, which is keyed to the shaft. Now you say, this is keyed to the shaft, and this is free to move. There's a gap here. Why is that? That means that this is disengaged right now. With the high speeds going up to 20 miles an hour that the vehicle will be seeing, it's not going to be a good idea to keep this spinning the whole time because you'll burn up the internal parts of the winch. So we made a clutching mechanism. The way that was made is there's a set screw offset 180 degrees from the keyway and a small detent and spring with a little ball bearing. You can slide that on the shaft to actually engage the front wheel drive and power the front wheel.
Your teammate said that with the normal drive it doesn't go backwards, so I guess you were the backwards engineer, is that right?
Yes.
So the electric drive is what allows this thing to go in reverse. I would just like to zoom in on the mission and the vision of the BUV. This is Purdue, Ag and Biological Engineering, Machine Systems Engineering, solving problems that really matter in the big scheme of things.